Okay, so i-record ko na lang yung next part ng lecture natin and then para mas mabalik-balikan niyo siya. So we ended here last time showing you yung how or basically explaining how to read AFM diagrams. And ano yung meaning itong lines na to, these tie lines again, indicate yung compositions that are off in equilibrium. And at the same time, yung lines na to, yung solid lines here, denotes yung solid solution composition of a particular mineral. So garnet, for example, has a more magnesium variety and also a more iron-rich variety. And yung range of compositions na yun is shown by this line. Okay? I think one part that I missed out last time was explaining, as I mentioned before, nag-shift yung locations itong tie lines natin as prograde or retrograde metamorphism progresses. And for example, yung example ko kahapon, yung chlorite, here, this is a chlorite stability for this particular grade, but if we increase temperature, usually nas nagiging magnesium siya, so nag-shift siya papunta dito. If we take a look at yung effect niya at particular bulk compositions, again, yung bulk A, we'll have this one. I guess yung main concern would be si bulk C, for example. With increasing metamorphic bulk E, rather. So yung bulk composition E. So originally, meron kang chloride biotite. As prograde metamorphism progresses, yung chloride composition again moves to the right, becoming more and more magnesium. So, yung bulk composition naman natin, hindi siya nagbabago. Fixed siya. What changes is yung mineral assemblage that is stable for that bulk composition. So, initially, as you can see here, yung E natin contains only chloride and biotite together with quartz, muscovite, and water. With increasing metamorphic grade, mag-shift yung chloride natin to the right, and eventually, yung tie lines na yun, mawawala na siya dito sa E. What that indicates is that yung new assemblage natin will be garnet, chlorite, and biotite. If you notice, this is actually the shift sa Barovian series from biotite zone to the introduction of garnet. So garnet isograd in. So that may be that is one possibility for how we introduce new minerals dun sa ating bulk composition. Okay? That such reaction is at the same metamorphic grade, such reaction will be recorded in a rock with bulk composition E, but yung rock natin with bulk composition D, already containing garnet, chlorite, and biotite, yung composition or yung mineral assemblage niya will not change anymore. Okay? So I hope you get that part. Ganon din, for example, itong bulk composition G natin. Looking at this diagram, you have kyanite and biotite, but as prograde metamorphism continues, for example, yung biotite natin shrinks to ever more magnesium composition, and eventually, you can imagine na nawala na yung tie line constraining. I mean, itong tie lines na to is lost during prograde metamorphism, and eventually mag-shift siya towards more magnesium composition, so that finally, yung bulk composition natin G would be something more similar to bulk composition I, which contains staurolite, kyanite, and biotite. Ngayon, kyanite and biotite lang. Okay? So yan, I hope you get that part. Let's see, for example, let's see that again using these three AFM diagrams representing increasing metamorphic grade. Looking at X, bulk composition X, bulk composition Y, and bulk composition Z. Initially, you only have, sa bulk composition X, you only have chloritoid, almandine, and chloride. As prograde metamorphism happens, hindi nagbabago yung kanyang composition until eventually yung tie line between staurolite and chloride is lost, and instead, since sobrang magnesium na ng composition ng chloride, and instead yung new stability is staurolite with biotite. So yung at this metamorphic grade, yung bulk composition ni X changes from chloride hindi yung bulk composition. Yung mineral assemblage ni X changes from chloritoid, almandine to chloride, almandine and chloride to something more like staurolite, almandine, and biotite. Okay? Yon. Another important thing pala dito, ito yung shift ng in the Barovian series, hindi masyado nabigyan ng importance itong si chloritoid Chloritoid is a chlorite-like in terms of optical properties, kamukha siya ni chlorite. For example, ito siya, yung CLD dito. Yan. Mas mataas lang siya ng relief pero it's the same greenish color as chloride. Okay? Iba yung interference color niya, of course. For more information, you can look chloritoid up sa curve, for example. So anyway, yung important point dito is that from this AFM diagram to this metamorphic grade represented by this AFM diagram, there was a shift sa phase assemblage in equilibrium with each other. When initially you have almandine, chloride, and chloritoid, eventually this metamorphic grade, it's not chloritoid anymore, rather it's almandine, chloride, and staurolite. So yung yung bulk X natin becomes chloritoid, almandine, chloride, staurolite, almandine, chloride, and then eventually, dito nga sa highest grade, staurolite, almandine, biotite. Take note na at this point, wala nang chloride in X natin, but that does not mean na chloride is absolutely unstable in this metamorphic grade. Actually, in some bulk composition, you can imagine a composition that is highly magnesian, chloride may still persist. Yan, chloride may still persist, pero yung chloride na yun is highly magnesian. Okay? Another thing, yung Y natin, yung bulk composition Y, initially it has a composition of, or mineral assemblage of almandine, chloride, and biotite. At this metamorphic grade, same metamorphic grade as this X here, you can see na si X meron na siyang almandine, staurolite, and chloride again. Yung Y natin did not change yung kanyang mineral assemblage. Still almandine, chloride, and biotite kasi yung bulk composition niya is here. Eventually, at this metamorphic grade, yung X and Y natin has the same metamorphic assemblage, mineral assemblage, almandine, staurolite, and biotite. So, what the point is, if you remember yung concept ng metamorphic phases, if you have different bulk compositions, even among metapelites, as is shown here, you can have different mineral assemblages at the same metamorphic grade or PT conditions. Okay. Finally, let's look at bulk composition Z. If you look at bulk composition Z, initially it only has kyanite and chloride, together with, again, lagi yang may plus, quartz, muscovite, and water. Yan. And then, as dito sa metamorphic grade na to, na stable na si staurolite, since Z is only here, tie lines lang siya ng kyanite and chloride, walang magbago sa mineral assemblage niya. And dito, sa highest grade, saka lang may introduce yung kyanite dito sa bulk composition Z. So ano pa yung isa pang implication nitong AFM diagram? What it tells you is that even if metapelite yung bato mo, it does not necessarily follow yung introduction ng zones, ng isograds, the same as yung pinakita ni Barrow. Okay? The Barrovian series represents a particular bulk composition. Actually, it was Y. It's something similar to Y bulk composition. Yung Barrovian series natin, from biotite zone, it goes straight to from biotite zone, it sorry, this is garnet zone pala since may garnet ka na. So garnet zone, biotite, and then yung next na introduction is staurolite. That is the classic Barrovian series, diba? But what this diagram tells you is that actually, in other metapelites that is more aluminum rich, meron ka pang isang isograd before na i-introduce yung staurolite, and that is the chloritoid zone. Okay? And actually, yung Barrovian series natin is not representative of most metapelites. Most metapelites are more aluminum rich than the Barrovian Y bulk composition. So it's actually more like this X composition. So the point is that in most metapelites, yung Barrovian series is not applicable. Okay? And conversely, it's not always good to follow yung Barrovian series to estimate yung metamorphic grade mo. Kasi nga, depende sa bulk composition, you can actually be missing out certain isograds. Okay? Yan. Okay, so this photomite here shows chlorite, chloritoid, garnet, and kyanite. So you can imagine, this is quite peculiar rock. So ito is another special rock. So nandito ka definitely sa part na to kasi you have chloritoid. Pero you have chloritoid, chlorite, kyanite, and at the same time garnet. So basically itong tile line na to separating yung chloritoid and chlorite is not present for this particular rock. For this particular PT grade. So it's something like connected tong lahat ng tong fields natin dito. Right? So this is an interesting PT condition. Okay. And bulk composition action. Okay. Ano pa ba? Okay. So next is yung petrogenetic leads. So when we say, ito yung isa sa mga pinakita ko kahapon na diagrams. Petrogenetic leads are PT diagrams, pressure temperature diagrams, showing all univariant reaction lines and invariant points. So univariant lines, this is F equals 1. When the rock is experiencing or when the rock is located in at a univariant reaction curve, one of the reactants must be consumed first bago mag-move forward ulit yung reaction natin. For example, because of increasing temperature. Okay? Ito yung F equals 1 natin sa examples before. Kapag nasa invariant curve ka, this one, kunwari, an invariant curve is where F equals 0. Okay? Meaning, sorry, baliktad, mali yung sinabi ko kanina. Kapag mali yung sinabi ko kanina, yung univariant line or univariant reaction line, F equals 1. Okay? F equals 1, meaning, kunwari, imagine, let's take for example, ito, zaidite plus quartz equals albite. So if you have a blue schist that is increasing temperature or experiencing increasing temperature, pagdating niya dito sa curve na to, this is a univariant reaction line. And what this means is that upon reaching this point, yung rock natin will stay there unless one of the reactants is consumed, or if pressure is decreasing, going this way, for example, or temperature, sorry, nakakalito yung example. Discard ko muna. Isa pa. Ulit. Isa pa. Okay. So, let's take, for example, yung jadeite plus quartz equals albite. Coming here. Ganyan yung trajectory niya, for example. Upon reaching this univariant curve, F equals 1, as the temperature rises, yung rock natin follows this path. Okay? Kasi F equals 1 lang. Yan. So, as temperature changes, one of the reactants is actually being consumed. Okay? In a continuous reaction, which we will further discuss later. So in a continuous fashion, in a continuous reaction rather. So, and for example, at this point, let's say ubos na yung quartz ng bato natin, then you only have now 2 phases, so less 1 phase, and your degree of freedom increases by 1, so it can go on doing like this. Okay? So here, at this particular point, F equals 2 kasi one of the reactants is lost. Okay? So that is a univariant reaction line. What about an invariant point? Let's take, for example, this one. Okay? If, for example, yung bato natin containing, for example, ito lang muna pansinin niyo, itong curve na to. Ano bang mas maganda nga? Mas madali. Ito, sige. Sorry. Ito na lang sigurong, so, imagine muna natin. Alam ko na mas madali. For example, wala dito yung yung alkali lang remember na lang muna. Yung andalusite, kyanite, sillimanite reaction curve. Okay? Ito yung invariant curve, di ba? Tama. Ito yung invariant point rather. Ito yung invariant point ng andalusite, kyanite, and sillimanite. Yung kaninang example, if you have a rock that is being heated, kyanite-bearing rock that is being heated, pagdating dito sa point na to, you have no degree of freedom kasi you have, well, actually, you have 1 degree of freedom pala kasi this is a univariant reaction line. So F equals 1 ulit. So as the temperature rises, it is forced to rise this way. So as temperature increases, pressure must also increase. Okay? Kasi F equals 1. And at the same time, habang tinatravel niya tong path na to, kyanite is being consumed and transformed into sillimanite. And eventually, pag naubos na yung kyanite, then it can move on again like this. Okay? Following yung original path. So dito, F equals 2 na ulit. Equals 2. Parang yung scenario kanina. But what if yung rock natin intersects yung invariant curve na to? So dito sa invariant point, invariant curve, invariant point. So pagdating niya dito sa invariant point, you now have 3 phases, kyanite, sillimanite, and andalusite. So F equals 0. Okay? So F equals 0, all of the kyanite must be transformed, okay, to either andalusite or sillimanite. Since this is being heated, the rock is being heated sa ating scenario, then it must be, all the kyanite must be transformed first into sillimanite bago makaka-move forward yung rock natin. Okay? That is how invariant points work. Okay? A petrogenetic grid gives you all the univariant curves and all the invariant points for all polar compositions in the chosen chemical system. For example, this chemical system is NC-MASH. Sodium, calcium, magnesium. Magnesium is also considering iron already. Aluminum, silica, and water. So NC-MASH system. Okay? So for this particular system, which is most applicable for basalt rocks, ito daw lahat ng reactions that is possible. Okay? However, as we've seen before, dito, pinapakita ng chemographic diagrams natin, is that although this reaction, for example, is possible, yung ating shift from chloritoid to staurolite, although such a reaction is possible, not all bulk compositions would show that. Okay? If you look at Y, again, hindi niya ipapakita yung reaction na chloritoid staurolite. Okay? So, ang point is, sa petrogenetic grid, it will show yung chloritoid to staurolite transition, pero it may or may not appear sa actual rock mo. So, there is a variation ng petrogenetic grid which shows which reactions are actually applicable sa particular bulk composition mo. And that is what we call a pseudo-section. We won't go into detail that much. It's a pseudo-section. A pseudo-section is like this one. Okay? It's also a TT diagram or a TX diagram, temperature bulk composition diagram. But the important point here is that, meron pa ba akong example ng TX diagram? Wala. So anyway, this is a pseudo-section. In this particular case, it's a TX. Okay? Temperature and bulk composition. So what it tells you is that if yung bulk composition mo, yung magnesium number ng bulk composition mo is 20, for example, a bulk composition of 20 here, for example, would be, so A, F, N2M niya is 20% more iron-rich, or 20% lang yung magnesium niya, and 80% is iron. Kasi di ba, Mg number equals Fe plus Mg over Mg. So if your magnesium number is 20, ang ibig sabihin lang nun is that 80% yung iron mo more than magnesium. So roughly, that would mean roughly nandito yung iyong bulk composition. Okay? O, lagyan na natin dito sa center, dito sa line. So let's say na yan yung bulk composition mo. Eh kung ito yung bulk composition mo, then all these reactions na dinidiscuss natin kanina would not appear sa petrogenetic grid mo. Okay? Bakit? If we look at this diagram, first, from a chloride plus biotite, it will reach or it will intersect itong point na to, wherein it starts to form chloride, biotite, and garnet. So, garnet is introduced. And then, dire-diretso lang siya. Pagdating niya dito sa, pag na-intersect niya tong curve na to, it will, garnet and chloride will start to react to form staurolite and biotite. And finally, yung bulk composition mo is garnet or yung bulk, yung peak assemblage mo at the highest temperature would be garnet, biotite, and staurolite. Okay? Kaya siya pseudo-section kasi, as you can see, dito sa pseudo-section, straight lines lang yung fina-follow ng iyong curve, ay yung temperature, ng iyong bato. Hindi siya nagbe-bend parang real petrogenetic grids. Okay? Ano ba? Anyway, yung important point nito is that this pseudo-section is a variation ng petrogenetic grid which only shows yung applicable reactions sa particular bulk composition mo. Okay? So if you're, for example, looking at bulk X, it shows you yung all the reactions that will happen sa bulk X. Okay? So yung example ko kanina, ano bang mas better na example? Siguro ito, yung Y. So, taasan natin yung bulk composition ng, yung Mg number mo, for example, 30 or 40. Let's say, bulk composition mo is roughly 40, and magnesium number is equal to 40. So, if your magnesium number equals 40, so straight line, chloride plus biotite will become chloride plus biotite plus staurolite. So, chloride plus biotite, kanina, dito siya, 40. Ayan, mas maganda pala ito. Chloride plus biotite, eventually, chloride plus biotite plus almandine. Then magandang example. Anyway, iulitin one more time. Okay, isa pa. Arbitrarily. Okay, arbitrarily, let's select bulk composition Y. Okay? Tapos, roughly, estimate natin, let's say Y is around magnesium number 30. Okay? Estimate lang. So, magnesium number 30. Tingnan natin kung how it reacts. Magnesium number 20 na lang. Daya tayo. Magnesium number 20. Okay? So, kunwari si Y equals magnesium number 20. So, tingnan natin. At this grade, you only have chloride and biotite, for example. Kunwari, meron tang thionine pa dito. Okay? So, una, kunwari, chloride and biotite lang siya. So, magnesium number 20, andito pa yon. Okay? As temperature increases, eventually, it intersects tong curve na to. Sa chemographic diagram, that would be like, the point na introduce yung garnet is when lumabas yung tie line na to. One more try. Okay. One more try. Let's say bulk composition A. Tignan natin gamitin si X. A na lang. Okay? This is bulk composition A. And A equals XMG 20. Okay? Example lang. So initially, yung ating bulk A, which is located here, XMG20, based sa chemographic diagram, it only has chloride and biotite. Okay? But as temperature increases, yung chloride natin becomes more magnesium. Itong tie line na to is little by little nawawala siya. Okay? So, first stop, ito muna. So, initially, you have a rock, bulk composition 20, only consists of chloride and biotite. As temperature increase, it intersects this point. Yung point na yon, yung intersection na yon sa chemographic diagram is the moment na itong tie line na to is lost so that yung bulk composition A natin is now exposed to the triangle almandine, chloride, and biotite. Okay? So, ito yun siya. Ito na yung A natin ngayon. Okay? Yan. So at this point, you know, as you noticed, wala namang reaction na nangyari. It's just that yung chloride and biotite tie lines changed because of increasing temperature. Okay? Next, if we further increase the temperature, eventually it intersects the point wherein you have garnet and chloride reacting with storolite, reacting to form storolite and biotite. Saan yun dito? If you look at here, sabi natin garnet and chloride reacts yan, to form storolite and biotite. So yung kaninang reaction itong ating almandine and chloride is superseded by a new tie line like this. Okay? So if you have crossing tie lines like this is a reaction. Yung reactants mo is yung original tie line, yung products mo pala, tama, yung reactants. Yung reactants mo is yung original faces connected by the tie line. So in this case, almandine, garnet, plus chloride. Yung products mo is the new tie line, storolite plus biotite. Okay? So yung ating bato, kanina, garnet plus chloride becomes storolite plus biotite. So yung rock natin kanina, here, kunwari dito si A, yan. It now introduces storolite dun sa yung assemblage so that now, finally, you have garnet, biotite, and storolite for this bulk composition A. Okay? In the timeline, in the tie line, in the chemographic diagram, again, itong tie line na to yung nawala. So that now, what you have is this new triangle, storolite plus garnet plus biotite. Okay? So, when you do metamorphic analysis or phase assemblage analysis like this, you have to have both petrogenetic grid and at the same time, AFM diagrams para malaman mo kung ano yung reactions that is applicable sa'yo. Okay? And yun yung gamit ng pseudo sections. Okay? It gives you para siyang simplified petrogenetic grid showing just the reactions that are applicable to your rock. Okay? Okay. I think that that was very helpful. I hope na intindihan nyo na siya. Tingnan natin, sorry, this particular petrogenetic grid is not for pelites. Magtingin tayo ngayon ng petrogenetic grid for pelites. So, looking at this rock, you have three bulk composition. Z is yung yellow dot, X is yung green dot, Y is yung red dot natin. So ito yung sinasabi ko kanina, not all reactions in the grid are applicable to the bulk composition that you are looking at. Let's say, for example, ito yung sa petrogenetic grid. Supposedly, yung sequence is chloritoid, magiging garnet, storolite, chloride, and then magiging storolite, biotite. Okay? Storolite, biotite. So, sino sa tatlong dots na to yung nagpapakita ng ganong reaction? Chloritoid, magiging garnet, chloride, storolite, and then magiging storolite, biotite. If you, sige, pause muna natin. Okay, so yung phase na yung bulk composition rather, na magpapakita lang nun is yung green dot, yung X natin. If you notice, yung X natin, here, initially meron siyang chloritoid, but due to the reaction, the reaction which is this one, yung chloritoid natin breaks down to form more garnet, storolite, and chloride. It now enters itong triangle natin. You have almandine, garnet, chloride, and storolite. And then, with increasing temperature, with increasing metamorphic grade or temperature, yung garnet and chloride natin reacts to form storolite and biotite. Yung kanina, same reaction. So yung X natin ngayon contains storolite and biotite. So ito na yan siya. Okay? With further metamorphic grade, yung chloride natin can be lost. So storolite chloride opens up to become kyanite and biotite. So kyanite and biotite pag wala na tong chloride entirely. Okay? So yun yung for X. Tingnan natin kung ano nangyari kay Y. If you have a bulk composition Y, it stays almandine chloride biotite, almandine chloride biotite, and then finally almandine storolite biotite. So, yung bulk composition Y natin, did not see this reaction. It did not have chloritoid in the first place. It did not, what the only reaction that it saw was this univariate curve here. Okay? And tingnan naman natin si Z. Si Z initially is chloritoid, kyanite, and chloritoid, kyanite, and chlorite. Some of the chloritoid becomes staurolite. So staurolite, kyanite, chlorite. Pero wala siyang garnet. So this reaction is not also reflected in this rock, si Z natin. So only bulk composition X shows you the reactions reflected dito sa petrogenetic grid. Yun yung gamit ng pseudosection. Okay? The pseudosection only gives you kung anong reaction yung applicable sa bato mo. Okay. So, and at the same time, ganun din magbasa ng petrogenetic grid in congruence or together with your chemographic diagrams. Okay? So yun yung ending. I hope you learn kung paano kung paano magbasa ng petrogenetic grid at ng AF ng chemographic diagrams. The next slides would be discussing na yung reactions that affect yung ating metamorphic rocks. Okay? Okay, for the next part, we'll be talking about reactions that that we observe in different metamorphic rocks. Okay? And from time to time, we will see yung pinag-usapan natin kanina, how to interpret ACF diagrams, or rather chemographic diagrams, petrogenetic grids, and the subtype of petrogenetic grids, pseudomorphs. Okay, so of course, yung isa sa simplest reactions in metamorphic minerals is yung polymorphic transformations, wherein you have same component, same, kunwari, for in this case, aragonite and calcite are both calcium carbonate, CaCO3, but they with changing pressure and temperature, they transform polymorphs. So for example, here you have an aragonite. If pressure drops, it reaches this, or it intersects this curve. This is a univariate curve. So upon if you have C equals 1 minus 2 phases, aragonite and calcite, plus 2 equals 1. So yung degree of freedom mo is 1. As you go down, so as you further decrease the pressure, it must follow itong line na to, univariate curve, until maubos completely yung aragonite, in which case, pag ubos na yung aragonite, yung number of phases mo na is reduced to 1. So 1 minus 1 plus 2, your degree of freedom becomes 2 again, so you can go down again. Okay, so that's the simplest polymorphic transformation. That is how polymorphs work. And it also explains to you kung bakit sometimes you have metastable minerals like aragonite, for example, coexisting with calcite. It just means na hindi pa complete yung reaction ng bato na tinitingnan mo. Okay? Yan. So, polymorphic transformations are reactions that are dependent on temperature and pressure. Another example, of course, is yung aluminosilicate, yung kyanite, andalusite, and sillimanite, as well as yung different polymorphs ng quartz, as well as different polymorphs ng carbon, which is carbon, graphite, at saka diamond. So, ganun din yun. If you have C, for example, if we as we continue increasing the pressure, yung graphite natin has to transform to diamond, pero F equals 1. So if we increase the pressure, temperature must also increase this way until maubos lahat ng graphite, ma-convert to diamond, and then saka na siya mag-move forward. Okay? So if the curves are accurately measured, we can use, the curves can be used to determine yung rock's PT, pressure and temperature, because of this characteristics. For example, if you only have calcite, you know that you are below this curve. If you have both aragonite and calcite, then you know that you are somewhere along this curve. If you have, for example, a way to determine temperature, for example, you know, you independently determined na yung temperature ng bato mo is 500 degrees Celsius, then, and you have on that rock both aragonite and calcite, then conversely, you know yung pressure mo is somewhere around 1.2 gigapascal or 12 kilobars. So, ganun siya. Yun yung mini-min nitong, if the curves are accurately measured, this can be used to determine the rock's pressure and temperature. If two phases are stably coexisting, then you must be in a univariant boundary curve, as I have explained before. So note that since different in entropy and volume for most polymorphic transformations, there is little driving force for the reaction to proceed actually. So that metastable relics are actually common. Here you have, for example, as an Andalusite, um, which is surrounded by silimanite fibers shown in yellow arrows. Yeah. Ito yung more better picture by Kawakami et al. 2001, Kawakami rather, 2001. Here you have Andalusite replaced by Silimanite, which is in turn replaced by Muscovite. This is another transformation type, replacement na to obviously. Pero for now, ang concern natin is yung polymorphic transformation, incomplete polymorphic transformation from Andalusite to Silimanite. Okay? Next type of reaction is exsolution reaction. So exsolution reactions, the same, similar to roughly, same process. So when you decrease pressure and temperature, some of the rock in question may reach a solvus. So for example, rock A, upon reaching this liquidus, it starts crystallizing this particular mineral until it eventually reaches point D, in which case it's all solid, so single feldspar ka na. But as you further decrease the temperature, it starts reaching or intersecting itong solvus, in which case, yung initially single feldspar mo starts to form another feldspar within the same grain. So this, for example, is the reason why we have perthitic and antiperthitic textures, diba? Yan. So this happens when a solid solution encounters a solvus, usually as pressure and temperature or temperature decreases, which results to the unmixing of the solid solution into distinct phases. For example, yung aluminum alkali feldspar and yung ating sodium-rich plagioclase feldspar, which results in the formation of perthitic texture. Yeah. Another example shown here is the OPX-CPX solution. So here, published by Pasco et al. In 2019, you can see this clearly OPX, and then along the cleavage traces, you have this CPX. This indicates na before this is due to decreasing pressure. So because of decreasing pressure, yung originally single pyroxene natin, solvus, yung single solid solution pyroxene natin, eventually transformed or eventually exsolved CPX along the cleavage traces. Take note that X solutions are not necessarily of the same family. For example, high pressure pyroxenes may incorporate aluminum, which at lower pressures may actually exsolve garnet or plagioclase. So pyroxene exsolving garnet or plagioclase. It's not really garnet or plagioclase that's exsolving, but rather the aluminum from the pyroxene. Okay? And eventually itong aluminum na to, yung aluminum na to is used to create garnet and plagioclase, or plagioclase rather. So usually, yung X-solution reactions natin are easy to spot because they are crystallography controlled. So for example, yung kanina is a CPX. This is constrained or mainly found along cleavage traces. Ganun din yung perthitic and antiperthitic texture. It's also crystallographically controlled. Next reaction is solid-solid net transfer reactions. Versus polymorphic reactions, the solids only of different the solids involved in this reaction have different compositions, so it involves transfer of material from one side to another. For example, if you have jadeite and quartz, yung example ko kanina dito, yung example ko kanina dito, hindi pala. Saan ba yun? Ito, dito, yung kanina. Yung ganyan, tapos ganyan, tapos ganyan, for example. Okay, jadeite plus quartz equals albite. So, this is a solid net transfer reaction. It involves the breakdown of jadeite and quartz, redistribution ng sodium, aluminum, and silica to form albite. Okay? So, uh, versus what versus another type of reaction, solid-solid ion exchange, i-discuss mamaya. Solid-solid ion exchange involves the progress of net transfer results to change in amounts of phases involved. And if diffusion is a limiting factor, kung kunwari temperature is too low or the temperature is too low to promote effective diffusion, or if wala ka masyadong pore fluids so that diffusion is very slow, these reactions may be arrested, forming yung ating forming yung ating coronas or yung ating symplectites, for example. So another example ng solid-solid net transfer would be enstatite, anorthite. Enstatite plus anorthite equals diopside, sillimanite, OPX, and plagioclase. Take note that solid-solid net transfer reactions are actually very good geothermobarometric tools. Usually, what you have is the incomplete transfer ng magnesium and iron, or magnesium and calcium, for example, from enstatite to anorthite to form diopside and sillimanite. So that instead, what you have is actually enstatite, anorthite, and some diopside and sillimanite. So when you do that, or when you have that, you can use yung parang in-explain ko na before, yung K, yung distribution ng components like calcium, aluminum, magnesium between enstatite, anorthite, diopside, and sillimanite to transform this mineral chemistry ng enstatite, anorthite, diopside, and sillimanite into PT curves, pressure and temperature curves, to know kung, kunwari, this is K equals 0.01, this is K equals 0.02, with each K representing a different ratio of calcium, magnesium, aluminum in enstatite, anorthite, diopside, and sillimanite. Okay? Or something more simple. For example, wala pa lang something more simple. This is also complex. So, but anyway, the important thing here to note is that itong solid-solid net transfer reaction can be used for geothermobarometry kasi usually what you have is both the reactants and the products, and by using mineral chemistry information of the phases involved, you can calculate K, and from K you can calculate PT. Okay? Mamaya na tong bullet na to sa dehydration reactions. A subgroup of solid-solid net transfer reaction is discontinuous and continuous reactions. So, narinig nyo na ito kaninang discontinuous versus continuous reactions. Pag sinabi natin discontinuous reaction, this is a reaction which tends to run to completion at a single metamorphic grade where the PT crosses the univariant reaction curve. Okay? Or actually, invariant point. So yung examples ko kanina, wherein you have jadeite reacting with quartz to form albite, yung final point, so this one for example, from here to here, you have both the reactants existing with the product, jadeite and quartz, existing with albite, and jadeite slowly or quartz, for example, one of the reactants getting less and less in amount, okay? Pwede rin yung mineral chemistry nila is changing until eventually maubos yung isa sa mga reactants, for example, quartz, at which point, saka na mag-move forward yung PT path natin. In terms of the rock, pagdating niya sa point na to, mawawalan ng isang phase, so for example, quartz, and you're left with the product plus a metastable reactant, for example, jadeite. Yung point na yon, yung point kung saan naubos yung isang reactant, that represents a discontinuous reaction. Meaning, it was a reaction that led to the consumption of one of the reactants. Along the way, before reaching that point, yung point na to, papunta dun sa final discontinuous reaction, the reaction was actually more continuous. Okay? Continuous kasi you have both the reactants, jadeite and quartz, coexisting with albite, and the quartz concentration getting less and less as you get more and more albite. So that's a continuous reaction. Okay? So what's the main difference between discontinuous and continuous reactions? Discontinuous reactions tend to runs to completion at a single metamorphic grade until one of the phases is lost. Okay? So it involves the abrupt change from the reactant assemblage to the product assemblage. When solid solution is pronounced, ang nangyayari instead is continuous reaction. Okay? So in practice, presence of reactants versus products plus, sige, wag na to. This is for the grad class. Okay. So yun yung, yan yung examples ng discontinuous and continuous reactions. Ano yung iba pang examples ng discontinuous and continuous reactions? We've seen both here, actually. So here, you have yung chloride composition mo getting more and more magnesium with increasing temperature. That is another continuous reaction. So you have the reactants chloritoid and chloride, breaking down and giving and chloride getting more and more magnesium. Until eventually, yung kanina kong example, so until eventually, sobrang naging magnesium na yung chloride mo, and a new tie line is formed, connecting staurolite and biotite. Here you have almandine, garnet, almandine plus chloride equals staurolite and biotite. This is a discontinuous reaction kasi the reaction will only proceed, or staurolite and biotite will only be formed when one of these phases is completely lost, in this case, chloride. So nung naubos na yung chloride, a new tie line emerges wherein you have staurolite and biotite. Okay? In lieu or in replacing yung original tie line, which is garnet and chloride. So you see, yung point is that sa chemographic diagram, sa petrogenetic rates, it both shows how continuous and discontinuous reactions proceed. Okay, more on that later. Next type of reactions are devolatilization reactions. So devolatilization reactions either releases or consumes volatiles like water, carbon dioxide, etc. Carbon dioxide and water yung pinaka-main kasi siya yung highest concentrations. But of course, you also have this volatiles. So other volatiles like brines are important, for example, in anhydrous conditions. So for example, granulite facies. So how does the volatilization reaction affect your location now reaction curve? For example, take this reaction, muscovite plus quartz equals aluminosilicate, alkali feldspar rather, alkali feldspar plus aluminosilicate, for example, kyanite, kaya sillimanite o kaya andalusite, but for sake of example, let's use kyanite, and water. Okay, so if the reaction, you see in this reaction that water is actually an component that is limiting the reaction, meaning it's not completely mobile. Okay, remember yung lecture natin or yung discussion dito sa what it means to be perfectly mobile for volatiles. So in this particular example, the fluid, water, is not completely mobile. Okay? Instead, it is needed for the reaction. So what happens? If yung amount ng water, okay, that is present as volatiles is not equal to the pressure, lithostatic pressure, meaning, kunwari, sige, ito mo ng scenario na to, where the pressure of water is equal to P lith. That means na lahat ng available spaces in between grains, kunwari, this is grain 1, grain 2, lahat ng spaces available sa grains, in between the grains, is filled with water. That is, yan yung minimi natin na P lith equals pH2O. If hindi ganon, if for example, tiny film lang yung water natin along the edges of some grains, hindi siya completely filling ng pore spaces natin, then pH2O is less than P lith. Okay? And as you can see, yung location ng reaction curve natin, itong muscovite plus quartz equals alkali feldspar plus aluminum silicate plus water, shifts towards lower temperature. Okay? Meaning, for example, if yung amount mo lang ng water is 1/10 the available space, yung temperature that is needed for the reaction to proceed is actually at much lower temperatures. So for example, muscovite plus quartz, rather, alkali feldspar and aluminum silicate reacts immediately at low temperature to form muscovite and quartz, for example, kung retrograde. Kung prograde, the reverse is true. Yung muscovite and quartz natin at roughly 400 degrees Celsius, starts to break down at this temperature because P lith is much less than, or P water is much less than P lith. Okay? If for example, yung amount ng water natin is 1/5 lang compared dun sa available space, kanina 1/10 kasi 0.1, ito 2/10, so 1/5. 1/5 yung available, 1/5 of the space is filled with water. If that is the case, then yung ating temperature or yung ating reaction, muscovite plus quartz equals alkali feldspar, aluminum silicate water, will happen at much higher temperatures, around 400 or 500 degrees Celsius. Kapag even more, kapag 0.4, so 4/10, 2/5, no 2/5, 20%, 20, anyway, 20%, ito pala kanina ay 25%. Kung 20, kung more, anyway, 4/10. 4/10 kung 4/10 ng available space is filled with water, then the reaction proceeds at a much higher temperature, so on and so forth. And again, you can see here, yung maximum temperature for the reaction happens kapag pH2O equals P lith. Okay? Yon. So, these reactions therefore depend, reactions like this, which involves water, either on the reactant side or the product side, breaks down or happens depende sa presence ng fluid natin. Amount ng fluid natin rather. Isa pa. Hindi pala okay. So, ulitin ko lang yung reaction, but this time looking through the lens of muscovite, for example. So muscovite, yung kanyang chemical formula is this one. It has OH. Okay? So, kung yung pore spaces in between muscovite grains walang water, then muscovite is forced to immediately react with quartz to form water so that it fills yung available space natin. Okay? That's why it reacts much earlier kapag mas mababa yung amount ng water natin sa pore spaces. Okay? If on the other hand, yung pore spaces naman natin is completely filled with water, then yung muscovite natin can take its time. It's not required, or it's not being forced to immediately break down to form water para mag-fill ng spaces. Okay? So you can think of it that way. Yun. So I think that's the best way I can explain kung bakit nagbabago-bago yung position ng reactions natin. Depende sa amount din ng partial pressure, amount din ng volatiles natin. So what this tells us is that uh, reactions which involve volatiles are always yung location ng reaction na yon is always dependent not only on P, T, X, but also partial pressure of volatiles. Right? Let's see more examples. So the location of the isograd based on the volatilization reactions is sensitive to partial pressure of the volatile species that is involved. For example, ito yung this is a PT diagram, this is a TX diagram. It basically tells you the same thing. This TX diagram is a slice of the temperature of the curve. Muscovite plus quartz equals KFS, alkali feldspar, aluminum silicate plus water, set at P equals 0.5 gigapascal, right? So, if for example, as you can see from here, if for example yung amount ng fluid is equal to the pressure of the fluid is equal to the pressure of the rock, then the reaction progresses at the maximum temperature, okay, of around 600, 700 degrees Celsius. If, for example, mas mababa yung amount ng water sa pore spaces than the available space, then the reaction happens earlier kasi nga muscovite basically has to dish out yung muscovite. Muscovite rather, has to dish out water. So you may ask, ano yung factors which may lead to water being less than the pressure of the lithostatic pressure? One way is if you have other components diluting yung water sa porous spaces. So for example, carbon dioxide. Okay, so ano sinasabi ko kanina? So one way kung bakit hindi equal yung pH2O sa pilit is if you have other components like carbon dioxide. So if you have, for example, here, you have 20% CO2, 80% water, ito na yung location ng reaction mo. If you have 50% water, 50% carbon dioxide sa pore spaces, then the reaction will happen here, so on and so forth, at this particular pressure. Okay? So that is one way kung paano siya nadadilute. So, further complexities arise kapag meron kang other so that was a reaction involving water as a product. Water as a product. What if you have water as a reactant, carbon dioxide as a product, carbon dioxide as a reactant? Ayun yung dinidiscuss nitong curves na to. Okay? I-discuss ko pa ba to? Sige, discuss natin. Okay. So yung example na diniscuss ko kanina is what we call yung muscovite breaking down to aluminosilicate, alkali feldspar, and water is a classic type 1 dehydration reaction. So it's a reaction which follows path like 5. Right? It follows path like 5 kasi this is XCO2. XCO2 is the reverse of XH2O. So XH2O, you can think of it as the reverse of 1 minus XCO2. The reverse. So for example, the higher the carbon dioxide in the interstices, the less water you have. So ganun siya. So for example, itong kung papansinin nyo, yung curve natin kanina, it looks like this because it's XH2O. Pero if it's XCO2, the shape reverses. So type 5. Yeah, type 5. Bakit? So, kung ito yung reverse, then H2O is highest here. H2O is actually 1 here, 100% water. And water here is 0%. Okay? So, let's mag-focus muna tayo sa reaction number 5. Sa reaction number 5, just like before, yung breakdown ng muscovite like this, which contains water, happens earliest kapag wala kang water sa pore spaces. Pag wala kang water sa pore space, meaning puro carbon dioxide, for example, yung nasa pore space, then it happens early. But if you have pure water at the pore spaces, then the reaction can happen later. So that is a classic dehydration reaction. The reverse is true for decarbonation reaction. Let's look at reaction 6. Not reaction 6, curve 2 rather. So let's look at, ito pala, sorry, not curve 5, curve 1 pala dapat gawin. Curve 1. So, but anyway, essentially same lang naman. 1 and 5. Mamaya, i-discuss natin yung 5. So curve 1, yun yung dinidiscuss natin kanina, but in reverse. So mirror image nito. Kasi nga, this is also mirror image ng x-axis dito. So that was curve 1. Tingnan naman natin yung decarbonation reaction. So as you can see, decarbonation reaction, ganun din, same concept. Decarbonation of a rock, for example, 2, this is 2. Yan. This is reaction 2 essentially. You have calcite reacting with quartz to form wollastonite and carbon dioxide. Parang before, if wala kang calcite or if wala kang CO2 sa pore spaces, kunwari yung pore space mo is completely filled with water, so dito 100% water, then the reaction happens very early. But if yung pore space mo is completely filled with carbon dioxide, ibig sabihin wala kang water, then the reaction happens at the maximum temperature possible, much later. Okay? So yun yung point. Okay, so that's reaction 1, check. Reaction 2, check. Paano naman kapag combined dehydration, decarbonation reaction? Yun yung curve 3. So curve 3 depends yung T max. So it depends yung T max sa ratio ng water and carbon dioxide that is produced. Okay? So for example, if we look at this reaction, magnesite plus salt equals forsterite plus carbon dioxide plus water. But the product is is always kung 6 yung particles, water particles mo, kung 6 yung volatile particles mo, isa lang doon yung water, 5 is carbon dioxide. So naturally, the reaction pushes the fluid composition towards more carbon dioxide rich side nitong TX diagram natin. So what it means is that if we have pure water, since this reaction produces more, or this reaction is most sensitive kapag wala masyadong carbon dioxide sa interstitial phase, then this particular reaction will happen much earlier kapag higher yung water natin sa interstitial fluid. Kapag masyado ring mababa yung ating carbon dioxide let me get back konti. Isa pa, burahin natin itong mga to. Isa pa. Dami ng kalat. Okay, let's think of it again in terms of the minerals reacting. Right? Lagi yung mas madali yan. Okay. Burahin ko lang to. Sulat ko ulit na mas maayos. Again, water Water is 100. CO2 is here 0, pero water here is 100. CO2 here is 1, so water here is 0. Okay, so let's look at this reaction. Here you have magnesite with CO3 and talc with OH or water. Kapag ka masyadong konti yung ating carbon dioxide ah, sa interstitial phase, meaning puro siya water, then magnesite breaks down early to compensate basically, to compensate and add CO2 doon sa interstitial phase natin. Kapag ka naman puro carbon dioxide yung nasa interstitial phase natin, talc breaks down to compensate for the OH so that in both cases, the reaction happens early. Yeah. So, question now is, when is the reaction occurring at the most ideal state or yung Tmax natin? Kailan na-reach yung maximum temperature? The maximum temperature is reached at this ratio equivalent to one part, ano ito? One part water, 5 parts CO2. So in arithmetically, 1/6 equal to anong ratio? Calculator na lang natin. 1/6 equals 16%. So, yung maximum natin is around 16% water. So, 16% water, 84% CO2. Parang mali yata. But anyway, something like that. Hindi yata to sakto dito. But anyway, something like that. Yung point nitong Tmax. So yung Tmax natin is controlled by the amount of CO2 and OH, yung ratio ng CO2 and OH that is optimal for this reaction. So that is reaction 3. How about reaction 4? Reaction 4 is a reaction which consumes water and liberates carbon dioxide. Here you have magnesite reacting with quartz and water to form talc, which releases carbon dioxide. So same logic basically. That's curve number 4. Look at curve number 4. So curve number 4, if water is concentrated, then magnesite breaks down early. Magnesite breaks down early to compensate for the carbon dioxide in the pore space. If the reaction is pure carbon dioxide, the reaction basically does not happen kasi wala kang water to begin with. Kaya siya nandito sa infinity. Okay? Again, yung magnesite, so this reaction occurs very early if you don't have water. If you have pure water, wala kang carbon dioxide, so H2O equals 100, so that magnesite immediately breaks down to compensate by adding carbon dioxide sa interstitial phase. On the other hand, kapag ka naman wala kang water, meaning CO2 equals 100, then the reaction never happens, so that the reaction curve goes to infinity. And the same is true for reaction number 5, which consumes carbon dioxide and releases water. If you look at a curve number 5, this one, kapag ka masyadong mataas yung water, pag masyadong mataas yung, it requires carbon dioxide kasi. So if you don't have carbon dioxide, meaning H2O equals 100, then the reaction basically never happens. Kasi wala ka ng reactant eh. But if you have too much water, so itong wala kang CO2, you only have if you have too much water, then this is not too much water. This is zero water. H2O 0, 100% CO2. So if you only have CO2 sa interstitial phase, then zoisite breaks down immediately to compensate by adding water sa system natin. Right? So that's how you interpret these 5 curves. This is a TX diagram, but you see yung shapes nila is like this sa PT space natin, sa PT diagram. Okay. Okay. So ito lang yung summary nun. Ayan, this slide is basically summarizing yung pinagsabi ko sa inyo kanina. A carbonate phase breaks down at very low XCO2, meaning very high H2O. Whereas a hydrous phase like muscovite will break down at very low waters. So just like curves 1 and curves 2. Curve 3, phase A, both has water and carbon dioxide, so breaks down only at very high and very low XCO2 when the carbonate component or the hydrous component becomes unstable. Curves 4 and 5, you have water and carbon dioxide becoming the limiting agent. If 4, the higher the XCO2, the higher the temperature is needed and vice versa. If reaction has no volatile, then it's horizontal line in this reaction, in this TX diagram. So if you notice this curve here, this curve here is hindi siya linear, hindi siya straight line kasi this is dependent sa CO2. But if you look at reactions which do not rely or which is not dependent on water, like this one, for example, this curve here, yan, hindi yan nag-require ng water, it's a straight line. If you look at jadeite, quartz, albite, hindi siya nagpo-produce nor consumes water, so it's a straight line. Okay? In reverse, if you look at reactions which include water, they are curved in this petrogenetic beam. Okay? So ganun yung itsura nila. Okay. So next, next, another important thing sa devolatilization reactions is if the fluid is completely mobile or if the system is open or closed. Dito pumapasok yung concept ng buffering. Sige, discuss natin kasi may pictures ako ng bato. Okay, so if a system, reactions may involve potentially mobile fluids and pressure temperature depends on the mobile fluidity, potentially involve mobile fluidity, and it's dependent on, one more time. Reactions involving mobile fluid is dependent on pressure, temperature, and physical properties of the rock. So what does it mean? If basically, meron kang rock which is permeable, and let's say ito yung rock natin, na permeable, and meron kang water reservoir sa baba. Okay? So this one, P lith is equal to PH2O, for example. Okay? So let's say the reaction that we are talking about is, or PCO2 na lang. CO2 na lang to. Try natin. PCO2. Okay? Okay. So for example, let's look at this reaction. Tremolite plus calcite plus quartz equals diopside, carbon dioxide, and water. So ito yung type, kanina, itong type na to. Yan, it produces both carbon dioxide and water. Okay? So, ito mo ng diagram, ito mo ng curve na to. If for example, ito dito yung tremolite and calcite and quartz natin, okay? And then the scenario is that meron kang fluids basically passing through this rock. Okay? And that fluid composition, for example, is set at 0.2. XCO2 equals 0.2. Okay? Yan, 0.2. So, in an open system environment wherein this rock here is open, okay, it freely allows yung overwhelming contribution ng fluids from this reservoir, so that it keeps the composition of the interstitial fluid at x equals 0.2. Then what happens is that as the rock, tremolite, calcite plus quartz intersects this point, okay? Yung curve natin, itong first curve, magre-react yung tremolite, calcite, and quartz to form diopside, carbon dioxide, and water. Okay? So uh, you have here, since completely mobile yung fluids natin, yung reaction natin, okay, so in this particular, sorry, this is closed system. Let's talk first about open system. So pag open system, yung such that yung composition ng fluids natin dito sa taas na bato is maintained at 0.2, then what happens is that um, the amount of reactants, tremolite, calcite plus quartz, is exactly equal to the amount of the products, like dioxide, carbon dioxide, and water, and you don't have a degree of freedom. Okay? Meaning this point here becomes an invariant point. Take note na at this point, hindi natin kinakount yung fluid phase na nasa reactant side kasi ito yung case na diniscuss natin before, wherein you don't include reactants. Perfectly mobile components controlled by external rock systems are not counted as C. Hindi siya counted as C. Okay? So sa reactant side, although you have water, of course, here, hindi natin siya binibilang. Okay? So that is for the open system. So every time it encounters these curves, it acts as an invariant point, so that bago mag-proceed yung reaction, tremolite, calcite, and quartz must be consumed completely, or at least one of the phases must be completely consumed bago siya maka-move forward ulit. Okay? And then, so from here, for example, quartz is lost, okay, tremolite rather. Okay, tremolite is lost. So once tremolite is lost, you now have diopside plus calcite plus carbon dioxide, plus carbon dioxide and water. But again, carbon dioxide and water is not counted kasi externally buffered nga siya. So yung composition niya remains at this point until it reaches this curve, in which point it's another invariant point, invariant point. It becomes another invariant point. So ang mangyayari is magre-react lang yung calcite and quartz to form wollastonite and carbon dioxide. Still, yung fluid composition is maintained at 0.2. So that is for open system. Somehow you have the interstitial composition you have the composition of the interstitial fluid maintained at this particular concentration, and that can be due to, for example, a larger reservoir controlling yung amount, or a larger reservoir ng fluids keeping yung concentration ng pore fluids natin at that particular point. What if the system is, so ito yung sabi ko kanina, let's start with the rock, tremolite, calcite, and quartz at low temperature. Yung intergranular fluids niya is 20% mol carbon dioxide and 80% mol water. And then we heat up the system. Yung case na dinidiscuss ko kanina is an open system. So you have a fluid that is perfectly mobile and externally controlled. Every time the curve or the reaction, or our rock rather, a rock that's being heated intersects a reaction curve, the degree of freedom is equal to 0. It's an invariant point. So one of the reactants must be completely lost first. Okay? Yon. And then, bago mag-proceed yung ating reaction. So next, tatawid siya dito, and then tatawid lang siya dito. Paano kapag ka-closed system? Paano kapag wala kang external reservoir controlling yung ating interstitial phase composition? So if that's the case, what we have is a closed system. So sa closed system, so As the reaction progresses, so for example, yung kanina, A, upon hitting this point, the reaction, tremolite plus calcite plus quartz, produces carbon dioxide and water. By how much? 3 parts carbon dioxide, 1 part water. Okay? So, kung over 100 to, 75%, this reaction, tremolite plus calcite plus quartz, produces 3 more times carbon dioxide than water. So it produces both, pero it produces more carbon dioxide and therefore pushes the composition of the fluid towards 75% and 75% carbon dioxide, 25% water. Upon reaching this point, around this time, ito yung Tmax. So dito na siya maglalast. Dito na siya maghihinto basically. So dito siya hihinto until maubos yung isa sa mga phase natin ulit. Isa sa kunwari quartz o kaya calcite, kaya tremolite. So for example, naubos yung yeah. So at this point, F again is equal to 0. So a phase must be lost and yan, a phase must be lost before magko-continue reaction. Pag kunwari naubos na yung tremolite natin, aakyat ulit yung temperature natin this way until it reaches again this point. This time, the reaction only produces carbon dioxide. Okay? So, basically yung water natin, di natin papansinin. But the important point here is that this reaction, calcite plus quartz, produces even more carbon dioxide so that eventually, yung ating composition ng fluid is 100% CO2. Or, that is kung mag-complete yung reaction. Of course, if for example, maubos na yung calcite natin dito pa lang, o kunwari, ubos na yung calcite natin here. So pag ubos na yung calcite natin dito, yung quartz natin dito, you have another degree of freedom and the reaction, the rising temperature pushes it upwards ulit. Okay? So, if in a closed system, the reaction of the rock buffers yung fluid composition natin to either higher CO2 or higher water, depende sa ano yung product ng reaction natin. Okay? In this particular case, it is being buffered papunta dito kasi binibilang natin yung fluid phase as another phase. So here you have water, since limited lang siya, hindi siya in excess, hindi siya completely mobile. So binibilang natin yung fluid phase natin sa 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 reactant side so that you have your 4 phases as reactants and then 3 phases as product. You have F equals 1. Okay? Yan. I hope you understand kung bakit dito F equals 0, you have the same amounts of reactants and products. Dito you have 1 extra more reactant. So in this particular case, the reaction is buffering yung X of any escaping fluids at XCO2 equals 0.75. Once a phase like tremolite is consumed, the reaction proceeds to C, where fluid X is again buffered by the rock towards higher XCO2. Ito na yung sabi ko kanina. So, if one of the phases is limited, reaction may run to completion before composition of pore fluid is stabilized and the reaction will cease before Tmax. So, yung sinasabi ko kanina sa open system, parang yung kanina lang din, what if, for example, tremolite happens to be consumed completely before umabot sa Tmax. So, kunwari, let's say at XCO2 equals 0.5, ubos na yung tremolite natin, then the reaction goes up, reaches this point, and then from here, it either, if meron itong reactants, calcite and quartz, then it proceeds this way until mabawasan ulit siya ng isa sa mga reactants, let's say quartz, saka siya move forward. Or if in excess yung calcite and quartz natin, then magko-continue lang siya endlessly. Okay, up to this point. Fluids can leave the TX reaction curve and the ultimate stabilized fluid composition, ATE, yun. Fluid, for example, can kunwari, so during this scenario, it's open Open system, yung hinanap kong term, open system. So, nababuffer niya all the way to the D. And then pagdating sa D, pwede lang din siyang maging closed system bigla. Kunwari, wala nang fluid from the reservoir keeping the system at that composition. Then the reaction just proceeds this way, something like that. Temperature interval of buffering is wider than unbuffered system. The temperature interval pala of buffered systems is wider than the unbuffered systems. Fluid is not perfectly mobile in the buffered system, and the reactant and product phases coexist in a continuous reaction. Anyway, kung to is basically yung pinagsabi ko kanina pa. Okay, so some examples. So here you have, for example, a calc silicate uh, showing tremolite out, diopside in. So this is a diopside quartz calcite rock. If you look at this diagram before, diopside calcite quartz rock. Yan. So tremolite is out. Posibleng ito yung path A to D, so buffered lang siya. Kasi wala kang tremolite coexisting with diopside. So yung kanina natin, sorry, yung pala yung implication ng isa pang implication nitong sinasabi niya dito na yan. Yung isa pang implication nung sinasabi kanina na if one of the phases is limited, the reaction may run to completion before the pore fluid is stabilized and the reaction ceases. So for example, yung kanina kong pinapakita na from path A, papunta siya dapat sa B, pero naubos na yung tremolite mo, then it can continue moving on this way. Okay? Moving up or down or up or following this curve. Habang inaabot niya itong reaction na to, here for example, you both have in this particular area continuous reaction, you actually have both diopside, tremolite, calcite, and quartz. So like this one, for example, tremolite, diopside, calcite rock. So we can think that this must be A, B, C reaction, pero hindi completed yung reaction. For example, here, you don't have quartz. So pwedeng quartz yung naging limiting agent mo. So you have tremolite, calcite, and the tremolite, calcite, and quartz reacting to form diopside. But then, quartz was the limiting agent. Unang naubos yung quartz. So, nung naubos na yung quartz, you end up with diopside, tremolite, and calcite. Tapos up this way, for example, so that you end up with this rock, tremolite, and diopside, calcite rock. Ito naman, diopside, quartz, calcite rock. Pwedeng tremolite was the limiting agent or pwede rin siya actually na buffered system. Naman. Unbuffered system, open system. Yeah, scenario. Okay, yeah. Okay. So, continuous reactions and discontinuous reactions are even more, also play out a role in other areas or in other scenarios. So, for example, okay, so continuous reactions. Let's take a look at this map, for example. So the dashed line here shows the isograd, garnet in isograd. So biotite to garnet isograd. All of these are metapelites. Okay, well, all of these and these are metapelites. And then, as you can see, yung location ng dashed line varies. So the location of the isograd changes. And madali lang siya i-explain based dun sa kanina nating discussion on chemographic diagrams, depende sa bulk composition ng each unit, yung location or when the garnet comes out maybe a function ng kailan siya maglalabas dito sa curve natin. So kanina yung ano yung biotite tapos garnet. So biotite na magkakaroon, I guess ito, si E. Biotite muna, tapos magkakaroon ng garnet. Ito. So, kunwari, yung scenario would be Y, this dot, this dot, this dot, and this dot. Yan. Of these three, yung una magkakaroon ng garnet una, biotite chlorite lang siya, pero yung una magkakaroon ng garnet, as temperature increases and chlorite moves this way, would be this one, followed by this one, followed by this one. So because of that, inherent differences, slight differences in bulk composition, as continuous reaction progresses, then when garnet appears first is a function of their bulk composition. So yun lang yung sinasabi nito. Okay? The difference in location, again, may be due to continuous reactions. The garnet forming reaction is the same, but at different points due to compositions, due to varying compositions of solutions, fluid, mineral, fluid yung kanina nating dinidiscuss. So if it's a fluid forming reaction, the location of the reaction may change. Yan. The location of the reaction may change. Depende sa fluid composition, or yung mineral composition is yung pinakita ko kanina. Yung dinidiscuss natin kanina sa AFM diagram na nag-shift yung chloride. Okay. Another possibility is contrasting composition resulting to varying garnet-producing reactions. For example, garnet may be formed in different ways. Here you have chlorite reacting with muscovite and quartz to form garnet. Other rocks may be recording chloritoid plus chloride plus chloritoid plus quartz equals garnet and water reaction. Both are garnet in isograds, pero the location is different for a rock with this reaction or a rock with this reaction. Okay? Yung important for us for this discussion is yung continuous reactions, which was discussed already previously. So again, just a quick review. If the reaction is discontinuous, F equals 0. So that a phase must be spent for the reaction to proceed at constant temperature. But since temperature and pressure are not independent, the one of the reactants essentially will have to be consumed at a single P&T if the reaction is discontinuous. If the reaction is continuous, the reactants and product coexist beyond the isograd, may coexist beyond the isograd, but their chemistry changes until one of the reactants finally disappear with increasing metamorphic grade. For example, ito yung chloride plus quartz natin initially. If FMG, or if let's look at a rock with XMG, magnesium number equals 0.5. Okay, as temperature increases, it intersects this curve, in which case it starts crystallizing, or it starts forming some chloride rather. Some chloride are spent to form garnet. Okay? Yan. Parang timeline lang to ng igneous rock. Okay? As temperature increases, yung chloride natin becomes more magnesian. At the same time, yung composition ng garnet natin also becomes more magnesian. And just like your igneous phase diagram, this is the lever which shows yung amount ng garnet continuously increasing until eventually wala na tayong chloride, which is marked by this one. This is the curve for chloride. Less and less yung kanyang amounts until finally, andito ko na sa dot na to. In which case, ubos na yung garnet, ubos na yung chloride, and you only have garnet, and the reaction or the temperature continue to rise. Can continue to rise this way. So this here, ito, yan yung continuous reaction. Ito naman, itong point na to is again the discontinuous reaction. So this is finally the point na wala nang mawawalan ka na ng isang reactant. Okay? This is a TX diagram. Let's look at that in a PT diagram. So if the composition of the bulk if the composition of the rock is at T1, so this is essentially the same. This essentially tells us the same thing, pero looking at the garnet magnesium number with, as the reaction progresses. So If, for example, we have a rock with initially chlorite and quartz, as temperature rises, for example, this way, o kaya yung arrow na red dito, this way, yan. Eventually, as temperature rises, yan, it forms more and more garnet, uh, and it consumes more and more chloride. So less and less chloride is available in the rock until eventually it reaches this point na yung XMG ng garnet is equivalent to the initial XMG ng chloride, 0.5. So that at that point, and at that point, mauubos na, or this is exactly the point na ubos na yung ating chloride, and lahat ng chloride is now completely transformed into garnet. So that if you look at the fields, initially you have chloride and quartz. Here you have both the reactant, chloride and quartz, plus the product, garnet, until it reaches this point wherein you only now have the product, garnet. Okay? Yeah. So, okay. Discontinuous reactions, these are the reactions which tend to run to completion at a single metamorphic rate. And in the PT diagram, whenever we have a rock exhibiting or intersecting a univariant curve, then that is the point na nagkakaroon ka ng discontinuous reaction. Let's look at, for example, yung Barovian series, specifically yung garnet, staurolite, and kyanite zone. So garnet zone transforming to staurolite to kyanite. So initially you have this shown here is an AFM diagram. Yung black dots are actual pelitic rock compositions, whereas yung gray field is the the distribution in terms of aluminum, iron, hindi pala aluminum pure yan, F, and M for most pelites. What it tells us is that during this period, or at this point, at this PT, garnet is actually stable. Okay, you can see here garnet is already included in the chemographic diagram, so it's already stable. Pero since you have this chloritoid biotite tie line, wala kang makikitang garnet in any of the rocks. Okay, so however, if wala kang chloritoid, kung wala tong tie line na to, for example, then these rocks here, itong konting iron-rich rocks, can actually contain garnet. But for now, although theoretically, pwedeng magkaroon ng garnet, in this particular rocks, wala kang garnet kasi meron kang tie line ng chloritoid biotite. Okay. Ignorin nyo lang muna itong ibang parts. Itong reaction curve na to, it's basically showing how pelites will react as it gets metamorphosed. Okay. For now, ang important is that if chloritoid is present, almandine may be created by this reaction, but we know that it's not going to be observed sa rocks natin kasi sa typical pelitic rocks, meron kang chloritoid biotite tie line. So, let's look at another way kung paano na-form yung garnet. Ito yung dinidiscuss natin kanina. Yung from here, we create a new tie line, garnet chloride tie line. That new tie line process yung chloritoid biotite tie line. So basically the reaction goes garnet plus chloride. This is the product. So you have chloritoid, yung pre-existing tie line is chloritoid plus biotite equals garnet plus chloride. Okay? Ito yun, chloritoid plus biotite equals garnet plus chloride. So you now have a new tie line. And for these rocks at least, and these rocks here, garnet is introduced in both pelitic compositions. So this is the garnet in curve for some minerals. So for some iron-rich pelites, chloritoid is present. For some aluminum poor, so this is actually chloritoid in. May chloritoid in as well. Di naman. So for some rocks, hindi nagbago yung phase assemblage nila. Well, nagbago pa rin. Garnet in pala daw. So this is, sorry. This is just garnet in curve. Garnet in curve. Yan. Ang point ko pala ay, for these rocks, this was garnet in curve. For these rocks, however, itong rocks na to, it was one, chloritoid, which initially was present. Ito yan sila, di ba? Initially, chloritoid was present. Due to the reaction, chloritoid was spent. So, chloritoid out siya. And at the same time, garnet in isograd siya. Okay? So, yon. So, ano pang important? Yung usual prograde hydration reaction resulting tie-line flip. Wag naman natin, hindi na natin ito basahin nyo na lang si Winter if you want to understand further how the rocks changes composition. Sige na nga. Unusual prograde hydration reaction resulting in tie-line flip, garnet chloritoid chloride, and garnet biotite chloride. Garnet chloritoid chloride and garnet biotite chloride subtriangles overlap. And yun lang pala sinasabi ko. Garnet can occur in these rocks at this period. Itong rocks na to. So, note the first appearance or final disappearance rarely reflects the absolute stability limits of minerals, but rather its overall stability range. So, yung sinasabi ko kanina na at this period, theoretically, garnet can be present in pelitic rocks kasi nasa AFM diagram siya, but typical phthalites won't show garnet kasi meron kang chloritoid biotite tie line. And instead, they will first show garnet kapag ka na-establish na tong garnet chloride tie line na to. And na-lost yung chloritoid biotite tie line. Okay, so let's look at that in more detail. Garnet zone in 4 types of rocks. So initially, ito yung chloritoid biotite tie line. Ito yung final garnet chloride tie line. So we can divide yung ating quadrants nitong reaction curves natin into 4. One was initially on the left side of this reaction, of this original tie line. Number 2, dito siya sa tie line na to, sa right side ng original tie line. Number 3, nasa left din siya ng original tie line pero below nitong bagong garnet chloride tie line. And 4, right side ng original tie line, below ng new tie line. So anyway, ang point lang naman ay tingnan natin kung ano yung changes sa mineralogy nila as the reaction progressed. Okay? So, sa 1, yung area 1 natin initially had chloritoid, natin laser pointer. Initially had chloritoid, garnet, and chloride. Okay? Hindi pala. Chloritoid, garnet, and biotite. After the reaction, it became chloritoid, garnet, chloride. Take note, yung biotite natin, bumalik siya, naging chloride siya. This is a reversal of the isograd, classic Barovian isograd. Diba? Sa Barovian isograd, chloride and then biotite and then garnet and then staurolite. Hindi pala. Chloride, biotite, and then garnet. Something like that. Anyway, so this is a reversal of the isograd from a biotite-bearing rock naging chloride-bearing rock. Okay? It's not common kasi sabi nga natin, wala namang, at least here, wala namang pellite na nagpa-plot sa area 1 nito. And it's not common. We wouldn't expect it, but it's theoretically possible. Yung nasa field number 2, ito yung makikita natin in some iron-rich pellites. And here you have chloritoid, biotite, chloride becoming losing biotite, mawawala itong biotite, and instead gaining garnet. Okay? So ito yung classic Barovian series. Yung 3 is another theoretical value or theoretical assemblage. First, it has chloritoid. It loses it after the reaction and instead gains chloride. And then 4, which is also possible in most pellites, it loses chloritoid and instead gains garnet. Okay? So sa ibang Barovian areas, it's not biotite transforming to garnet, but rather it's chloritoid transforming to garnet. Ganun yung isograds nila. Okay? Again, due to slight differences in bulk composition. So the minerals that are developed or lost in a rock at the isograph thus depend upon the bulk composition and do not reflect the absolute limit of any mineral involved. For example, some iron-rich pellets in areas 2 and 4 will therefore have garnet introduced well after the phase, garnet, is theoretically stable. Most pellets are not in 2 and 4, however, so that they are actually unaffected by the reaction. Most pellets, meaning most of this gray and itong mga dots, lahat naman sila or most sa kanila ay wala sa areas 2 and 4 and therefore will not be affected by the reaction. Okay, yeah. Most pellets are not in 2 and 4. Garnet in here is KF mesh is in KF mesh system only. However, actually some components like manganese stabilizes garnet even at lower temperatures. So this whole shape here gets changed kapag yung rock natin, pellite natin has an Mn, manganese. Okay? Anyway, hindi natin siya masyado tingnan. Another important, so that was continuous reaction. So the reactions were happening, well, this was a discontinuous reaction, but anyway, from here on out, nakikita natin na continuous reaction lang siya. Yung chloritoid becomes decreasing in abundance, chloride becomes more magnesium. Until eventually it starts, or staurolite starts to form. So iron staurolite is stable by the stabilized by the reaction between chloritoid and kyanite in the iron system. So, sorry. Here you have the chloritoid kyanite tie line, but then kyanite, staurolite rather. Here you have chloritoid and kyanite tie line, but once staurolite is stabilized, staurolite is between chloritoid and kyanite. So, chloritoid plus kyanite equals staurolite, right? So once that happens, yeah, as you can see, most rocks which may have had kyanite suddenly can lose it. For example, this strip here will have staurolite and chloritoid, thus mawawala yung kyanite nila. Right? I think yung important, yung gusto kong i-highlight dito, i-skip ko muna to kasi hindi naman siya, we won't go into the detail kung paano yung nagpapalit-palit yung Barovian zones. Gusto kong i-highlight dito is yung final, yung terminal reaction. So, chloritoid finally gives way to the chloritoid dito, di ba kanina? May chloritoid dito. Eventually, chloritoid becomes more and more magnesium. And then eventually, sobrang liit na lang nung stability ng chloritoid and eventually it's lost. So that now you have yung mas familiar tayo kanina pa, garnet chloride staurolite curve. Okay? If you look at kanina, yung itong rocks natin, yung assemblage niya is just chloritoid plus chloride. Okay? Plus ng staurolite. But eventually, itong chloritoid natin shifts papunta dito, yung composition. So, yung tie lines natin become ganyan. And eventually, staurolite and garnet reacts to form chloritoid. And, chloritoid is broken down into garnet and staurolite rather. Eventually shrinking to a point until eventually you have your minerals, you have the rocks exhibiting just garnet, staurolite, and chloride. And that is the chloritoid out curve. So this time, it does represent yung upper stability limit ng chloritoid. So here, you don't see chloritoid anymore. That means wala nang, kahit in theory, wala nang chloritoid na present. Okay? So that is around 590 degrees Celsius, 0.6 dito sa ating diagram. So here, you have the final curve for a chloritoid. So chloritoid here is eventually consumed and broken down to garnet, staurolite, and chloride. Wala nang chloritoid dito. Okay? Yon. Ano pa? Ang isa pang gusto kong i-point out is the same thing as the one before. ipakita ko lang ulit, ito nga yung kanina natin dinidiscuss pa, yung garnet chloride curve, um, garnet and chloride reacts to form a new tie line, staurolite and staurolite plus biotite. Yan. So this is the staurolite biotite schist. And as you noticed, although staurolite has been theoretically stable since this grade, yan, stable na siya dito, even higher temperature, stable na siya dito, pero never nagkasama yung staurolite and biotite kasi lagi silang divided by the garnet chloride tie lines. This is the first grade na magkakakita yung staurolite and biotite together. So some metamorphic petrologists are actually support the idea that instead of using individual isograds, which as you've seen by now, which as you know by now is already individual isograds may or may not appear. Paired isograds, for example, staurolite plus biotite isograd, definitely occurs only once. It happens only above this metamorphic grade here. So isograd, it's here, 0.7. So if you look closely, staurolite has been present here. You can even have staurolite here. Biotite may be present as early as 2, but biotite plus staurolite is never occurs together until 0.7. So 0.7 is the yung paired isograd ng biotite and staurolite in yung first appearance nila. So, yun. It's an alternative to the single mineral isograd. Two mineral isograd. Anyway, discuss na natin yung reaction. So, something like this, for example. Yan. Chloritoid out. So, chloritoid out, since chloritoid lies within the garnet chloride staurolite triangle, chloritoid simply disappears from the quartz-bearing AFM diagram, and its components are redistributed into the faces defining the triangle that surrounds it. In this case, garnet, chloride, and staurolite. The reactions that lose a phase entirely from the compatibility diagrams are, and rather than rearranging tie lines, are what we call terminal reactions. Terminal reactions meaning beyond this point, there will no longer be any chloritoid. Okay? And this also introduces yung ating staurolite zone. So for some pellets, at lower temperature, staurolite may be introduced by garnet plus chloride equals staurolite plus biotite at 0.7 nga kanina, producing a tie line flip in which garnet and chloride is lost and a staurolite biotite line is created. According to Carmichael, 1970, since this is the first time that staurolite and biotite coexist, this may be used as an alternative isograd. Yan. Individually, staurolite and biotite have wide range of stability, but together they only have, or they clearly point out to a single temperature. Something like this, for example. Ito naman yung pinapakita ko dito yung photomicrograph beautifully showing yung chloritoid out isograd. So here you have a garnet including chloritoid grains, red arrows, chloritoid grains in the inclusion, And then sa matrix, what you have is staurolite and kyanite. So, well, yeah, staurolite and kyanite, but the staurolite and biotite. So you can imagine chloritoid is out, garnet becomes stable with staurolite. So wala kang staurolite sa inclusion sa garnet kasi dati meron kang tie line with chloritoid. So instead, what you have is garnet and chloritoid. But once chloritoid is lost or once chloritoid is terminally eliminated, yung nasa matrix mo na is this reflects this new timeline of tie line of garnet and staurolite. So chloritoid is found in inclusion but not in the matrix. Other reactions are ion exchange reactions and oxidation reduction reactions. Siguro konti na lang to. Ion exchange reactions basically is solid solution. For example, the reciprocal exchange of components between two or more minerals, usually involving cations. For example, yung iron magnesium exchange between OPX and CPX. For example, the reactants enstatite plus Edinburghite equals ferrocylite plus diopside. O kaya yung iron magnesium exchange between garnet and biotite. Uh, Garnet and biotite, which is the anite plus pyro, anite being the magnesium, rather being the iron biotite, and pyro being the magnesium garnet, resulting to more magnesium biotite phlogopite, and more iron-rich garnet almandine. So how does it differ from continuous reactions? Yung modal abundance kapag ion exchange remains the same. It's just the chemical composition. Yung iron magnesium ratios lang yung nagbabago. Okay? Yan. So, of course, just like discontinuous reactions, ion exchange reactions are a function of temperature and pressure. Sometimes, for example, as we've mentioned before, generally with increasing temperature, garnet becomes more magnesian. Fluoride also becomes more magnesian. So, yon. Sa ano tong hindi ko na masyado i-discuss, I think too much information na yung geothermal barometry and yung blocking temperature. If you want to learn more about it, we'll have to discuss it in person. And finally, oxidation reactions, ganun din. Ito naman parang siyang yung fluids. So, buffering, pero due to the ability or mobility of oxygen. Depende sa abundance ng oxygen in the system, it may buffer the iron 3, and iron 2 into either iron being mostly in silicates, or if you have excess oxygen, iron may be turned into magnetite, and if it's very oxidizing, iron may be in the form of hematite. Okay? In the case of the examples that I've shown you before and yung I've discussed with you, hindi natin masyado nagamit itong buffering reactions for oxidation redox reactions. But I hope you guys understood by now yung continuous and discontinuous reactions and actually itong devolatilization reactions. Okay? Doon ako mag-focus. Sorry, hindi pala siya na-stop ko pala yung record. Anyway, so I was saying before, so kaya ko ni-record, this is the last lecture for 51, metamorphic reactions. After this, sa Tuesday, ang gagawin natin is a quiz on this topic. And doon na rin yung pinaka-review quiz ninyo for the law exam. Kaya ako siya ni-record para kung may tanong kayo dito sa chapter na to, we can discuss on Tuesday. And may time pa para sa exam nyo on Thursday. Okay. So see you on Tuesday next week.